Good. So good morning, everybody. It's a real pleasure and an honor to be here, to be with my friends in Indonesia. Today is a virtual, but hopefully I'll be in person a little bit later. So I was asked to give the first lecture, a general one. So basically my title is Biorefinery Concept and Implementation, Renewable Materials from Lignocellulosic. So this presentation will have two parts. The first one is the biorefinery concept and implementation. That would be short and that would be mostly, I would say, academic to give a general structure. And the second part would be the renewable material from lignocellulosic. So I'm going to show you some more, I would say, up-to-date example and hopefully to make you dream and open your mind and your creativity to see the endless possibilities with the biorefinery and lignocellulosic. So basically, that's what I'm trying to do. I was with you in Indonesia 4 years ago already, and I had a fantastic time. I discovered really, I made friends. And for me, one of the mystery is how can you remain so slim with such a beautiful and wonderful cooking and such a big generosity. I'm still trying to understand, but yes, that has marked me. But let's start the class. So everything starts with the light and with the photosynthesis, and that's what I try to convey on this graph. So on your right hand side here, basically in green, we see where we have all the photosynthesis. So we have on, we can say the continents, and we have Indonesia here, Australia here. And what you notice also is you have the ocean. We tend to forget the ocean, but there's a lot of possibilities. And basically, the amount of energy we get from the sun is something like 120 tetrawatt. So it's 10 to the 12 watt. So yes, it is a lot. But if you calculate and look at how much power is used by humanity, it is 16 terawatt, 16 to the 10 power 12. So it is a little bit more than 10% of what we receive, which is enormous. Basically, we consume too much energy. So we have to see what we can do about that. So to convert basically the photosynthesis to make the biomass, we rely on the photosynthesis. And here it's very simple. For an engineer, all chemistry is very simple. We have the light of the sun, basically the UV. We have some carbon dioxide from the atmosphere, and we have some water. And basically, what we have, we're going to convert the carbon dioxide plus water using the light of the sun to produce a plant, to produce some glucose that would then evolve into really a plant, and oxygen. So that's what is basically the essence of raw material. So now we're going to go through, and again, the reaction is we have the water plus the CO2 give us some glucose, and we form the tree. And we're going to have the tree and the forest and the field. And we must be aware of the question, and I will not go over that, but what are the possibilities? What are we trying to achieve when we grow a forest? Basically, it is the optimization between the economics, the job, the number of dollars, the P&D, the environment, and the social. And basically, we have to reach a social contract to maintain between, I would say, the recreation and between using the products, the timber, the wood for the paper, for energy, and so on. So this is an important part, and each country has a different, I would say, social contract. Indonesia has its own, Australia and United States have different one. So what we're going to look at today is basically go from the trees to some products. So we can go for the timber or the paper. I will not talk about the timber, but the paper will be my starting point. And we will see how can we evolve into, I would say, higher value, more structurally or chemically control and engineer product. So that's what we will look in our later second part of the presentation. But let's focus to Indonesia. And if you go on Wikipedia, that's what you can find. And basically, how important I would say is the forestry or the biorefinery in Indonesia. And already as we speak, or indeed 3 years ago, the biorefinery was representing 17% of the export of roughly $2 billion American dollars. So it is significant. And if you look, what we have is we have the palm oil, we have the rubber, we have the chemistry. So you have a very well integrated industry. We have petrochemistry, you have chemistry, you have wood and forest product, you have a very good agriculture. So you have tremendous opportunity. And as we speak now, it is 17%, but there's a lot of opportunities. And that's really what I would like to open to show what are some of the possibilities. But let's be a little bit disciplined before we really go and look at some of the new to the world or emerging application where Indonesia can play a role. Let's look basically at the concept of the biorefinery and its implementation. So what I would like to do in the next, I would say 15, 20 minutes is to give you a framework to analyze the biorefinery. So basically, first, let's give a definition of the biorefinery. When I mention biorefinery, what I mean is the co-production of energy, fuel, chemicals, and materials and food from biomass to optimize economics and sustainability. So why do we do that? I have three drivers. The first one is the environment. Really, we can mitigate the climate change, we can minimize the greenhouse gas. That's the first possibility. The second is economics. And economics in the last decade, it has gone all over the place. One would be to secure energy, basically to reduce the dependency on oil from other countries. A second is to migrate from a petrol to a bioeconomy, and also to reposition and update the manufacturing industry, and basically to come with new revenue from the forestry and the agriculture. So these are the economics. And the last is the social, basically to provide jobs and to migrate from, I would say, old industry to more sustainable and to develop the rural and the agriculture development. So basically, this is the concept of the biorefinery. Is it new? What are the drivers? I don't know if you look at the journal, that's a bit scary. It's already 21 years old, but the first one to send the alarm was The Economist. And some of you will recall this cover page, the end of the oil age. So it was in 2001, and we're really scared not to have enough oil to sustain us. And that was the first driving force, and that's when the biorefinery came, and especially the biofuel. How are we going to be able to replace oil if we're running out? So that was the first time we realized that our reserve of oil and gas and coal are limited. 5 years later, if you look at the front page of the Times, you had a little polar bear in Canada on a little shrinking piece of ice. And now it is be worried, very worried. And that's really when came the global warming and the effect of the CO2 and the warming up of the atmosphere. So that was a second driving force. And here the idea was to reduce the production of CO2 to mitigate the global warming. Also, we can see if you look at commodity, if you go into, I would say, refinery or pulp and paper mills, you produce typically one product. And here what I have is I compare, basically, it's fairly old, but I wanted to get that because we get the maximum. I compare the price of the barrel of oil as function of time. And you can see it was in 2005, it was in the 50s going up. And suddenly the global economic crisis came, and whoops, the price started to, we had some, no, the Iraq war, sorry, to increase, and we went to $127 a barrel of oil, and then it went down. So really to go from 50 to 127 as a raw material, it was very difficult for a lot of industry. And here what I plot is in dollar per ton, the price of the pulp of the ton of bleached eucalyptus pulp. And you can see it went to 850, and then just after that, when we had the economic shock, it went to a minimum of 450. So basically half of the profit, and then it slowly went up. So when you have a company that just produces one product and at 1 million maybe ton a year, we're very susceptible of the price. And if it's becoming a commodity and the price fluctuate, it's very difficult for the company to deal with that. So then came the idea of, can we have other products, higher value product, to reduce the dependency on the market? Is it a new concept? No, I don't know how good is your Swedish, but if you go on a Swedish document in 1945, what you have is basically the biorefinery, and you can read methanol, ethanol, benzene, and so on. So basically, it was at the end of the Second World War. Sweden had no oil, and they tried to make do with the wood. And that was the first example that I've seen of the biorefinery. Good. Now let's have an idea of scale. We're still in Sweden, and they had Gudrun, which is a hurricane that came and destroyed a large part of the forestry. And here they were very nice. They make us a nice picture. And here what I show you is 1 million cubic meters of wood. So it would be a little bit more than 1 million ton of wood. It would be something like 1.5 million ton. So basically what you see here is the wood requirement of a world-class pulp and paper mill. So that shows an idea. And if you go for 1 million ton a year, that's roughly, let's say, 5,000 tons a day. And if you want to compare that with a petrol refinery typically is 10,000 barrels of oil. So if we assume roughly a barrel is like half of a ton, basically we need something like 3 or 4 times this amount per year to feed one biorefinery. What does it mean? It means there's a disconnection in scale between the biorefinery and the current pulp and paper mill or the current forestry. Because in order to get 3 times that per year, we need a lot of forest. So it just brings a little bit in context if we use the wood for all what we have to expect. And also it can help us to see what is feasible, what is the best utilization of wood and bioresource for energy versus material versus chemicals. Good. So now I would go a little bit more, I would say, structure and fundamental to give you a basis. I would like to use my next 15 minutes to give you a concept of what is to basically classify the biorefinery. So whenever you have a biorefinery example or problem, how do you start? And basically, what are the commonalities? So we will go through that. And after we'll go to more, I would say, emerging example. So here what I use is the nomenclature of the IEA, the International Energy Agency, that have a task 42 that is dedicated to the biorefinery. And here, basically, we try to get a classification. So we classify the biorefinery in terms of platform, product, feedstock, and process. And let's look at that. The feedstock is the type of renewable biomass, the type of sustainable carbon we can use. The products is basically what is the main product of your biorefinery. Because here, a concept of sustainability, for each kilo of wood of lignocellulose, we want all the kilo to be used in a different array of product. So the third is the technology. What type of technology we use? So we have on one hand the biotechnology, so with the enzymatic hydrolysis and the fermentation. And we have on the other hand the thermochemical process and even the chemistry and mechanical treatment emerging. And then we have the platform, which is the sustainability, the family of substrate, process, and product. So let's look rapidly to each of these 4 different classifications that will help us to understand the commonality in biorefinery. Feedstock. Basically, you need some sustainable biomass, and there are 5 main types. The first one is basically the residue from agriculture. We think about the straw, the grass, the bagasse. But you can also go for the starch, the sugar, the oil, and the animal fat. But if you do so, you really come into the polemic of food for fuel. Is it ethical, or can we use food, what is used for food, for production of chemical? The second use is for forest. That means we have the lignocellulose, we have the hardwood, the softwood, the bark that comes from plantation or from the forest. We have also a third source of feedstock is industrial. So the recycled wood, the recycled plastic, the recycled fibers that we can use. From the cities, the urban, so the recycled paper, the municipal waste, we can do a lot. This is a very strong source of carbon that can be used. So that's a good source. And also the marine biomass. But basically here, what we do, we talk about sustainable carbon. We talk about the carbon that stays in the loop of the atmosphere. That means from the sequestration of the CO2 with the light and the water into glucose, and then that can be used. So that's the loop we're talking about. The second part of the classification is what type of products we go. So basically, we have four more types, major type of products. The first are the chemicals, mostly the alcohol, ester, a bit of acid, and phenol. The second are the materials. We can think about the pulp and paper, the wood product, and the polymer. And I'll try to give you more example of what you can do with some paper, or what can we do with some cellulose to make super absorbent and to replace some polymer. We can have food. Out of the biomass, we can provide a source of carbon for the fermentation. We can grow some proteins and all kind of different source of food. Or energy. You can take the wood, you can burn it, the residue, you can burn it, you can make liquid fuel, and you can recover. So these are the four types of products. Then we look at what type of process do we have. We have four types of main process. The industrial biotechnology, and we just had a presentation, a bit of that before. So we have the enzymatic hydrolysis, the fermentation, and you can also use the algae. We have the thermochemical process with the pyrolysis and the gasification. And I think you'll have a few talks on that a little bit later. We can go with chemical reaction, basically the synthesis, and the acid hydrolysis is one type, and we can do the esterification. So I'll show a few examples here, or the mechanical process. And you can combine, you can start with mechanical process, chemical reaction, biochemical, and so on. So we can permit the different type of process. Then we have the platform, and the platform is a little bit more difficult to understand. So they're defined as an intermediate connecting different biorefinery system and their process. And basically, we can have the C6, the sugar platform, from which we do the ethanol. We can have the syngas, from which we're going to do the Fischer-Tropsch reaction to do the diesel, and so on. So here, I give you an example. I take an example from Aventium for the furanic. I can take some lignocellulosic, I do a pretreatment, and I'm going to fractionate the lignin, the hemicellulose, and sugar, and the cellulose sugar. And I can do with the lignin to basically to have a combustion. I can take my C6 and C5 and to convert to chemical reaction to biofuel and chemicals. And if you want, you can calculate the index of complexity of a biorefinery. And here you give 1 point to each of the products, the treatment, the platform, and the product. So if I take globally to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, so to be a complexity of 13, which is fairly high, so higher risk. But that's, I would say, on the academic side. Good. And then you had the NREL, the National Renewable Energy in the States, that came with a scheme to use on the petrol refinery with what we can do with the biomass. So what you have on the left-hand side, you have the feedstock. So you have the starch, the cellulose, oil, and so on. You have the platforms, so the syngas and the sugars, and then the building block. You go from the syngas, the C2, 3 carbon, 4, 5, 6, and aromatic. And why do we stop at 6? The reason is very simple. 6 is the number of carbon that you have on the glucose. So it's difficult to make a molecule bigger than your constitutive element. So that's why we have 6. And then you have the secondary chemical, intermediate, and the product. And basically, what NREL has been able to do is to show that with the biomass and most of the chemistry we have now, we're able to replace pretty much all the petrol refinery. But that was in 2001. But the complete biorefinery has not been done. We had a bit of, I would say, evolution, more focusing, I would say, on selectivity and how you value products. And we discussed that. That closes my first part of the lecture. And I will now continue with the second, which is more, I would say, interesting, and I'll show you some of the example. And some of my colleagues will present more on the thermochemical process. We'll have an expert a little bit later on today, and so on. But today we'll focus more on the material, the fairly advanced material we can do from the lignocellulosic. So what I would like to do, I would like to address 5 questions. And because I'm long, we need to have a bit of fun together, so we'll try to enjoy it. The first, I present who we are at Monash and Biopriya. So I'll give you a small example to show where we are. And my point to show is it doesn't take a monstrous, the biggest universities. Anybody, any institute is able to contribute, and I'll show you who we are, and you'll be able to compare, and we're fairly small. And then we go in research. How can we make agricultural aids from cellulose? The second is how can we make cellulose biodiagnostics? I will then present a new optics on cellulose. And then I hope that out of that, you want to come and visit us at Biopriya and Monash and in Australia. And then you have a question, are you the beach type or the desert type? So these are the 5 questions we'll address and answer together. So let's start. This is where we are. So basically, our work is with staff and graduate students. During the COVID, we were locked down, and during the COVID, our institute was the task force of Monash for the COVID, and we did 2 things in 4 months. The first one is we developed a small diagnostic for the COVID, the SARS-2, and that was using the equipment of the blood test analysis, and I'll show you a few graphs. And that was the eureka moment. After months of failure, finally we had a success. And that was the team that did that. And the second is here you see us. Of course, we're hired for the look, but we made some paper gown. We were completely out. Australia was isolated. We have no polyolefin industry. So we have to find a way to make the non-woven and to make gowns out of paper. And we developed a laminated paper with which we can do, we did some paper gown that resist the COVID. So that was for the surgical good. And we work, this is my colleague. So I did none of the work. I present what the work of the colleague and student did. We're a small institute, so we see a small building. We have 7 labs and nothing special, just normal chemistry, engineering lab. Good. We work on 3 platforms, and I'll discuss about each of one a bit. So we're going to have diagnostic, and I present you that at the last time, and we had some progress, and I will show you that a bit. We work on biomaterials and also on sustainable solutions. Good. So what I will do now is present you a few examples of what we can do, some advanced application of cellulose mostly. The first one is our world is growing, and I think a few weeks ago, we just achieved 7 billion people on this earth. And you project to go in 8 within a decade, and basically to level off until 9 billion. That's a lot of people, and we have to feed everybody, and everybody has the same right of food. So what we're wondering is how can we contribute? How can we use the lignocellulosic to help our, I would say, industry, our agriculture industry? And that's, I will present you the work of Melanie that is being followed by a team. So what we want, basically, cellulose superabsorbent to try to help agriculture. Australia is the driest continent, and indeed it's a bit ironical. During the summer, we're way too dry, and during the winter, we had a lot of flood, and there's a big part of the country flooded. So what we would like is to be able to take one of a flood of water to help us to carry us through the drought. So that's what we're trying to do. So we would like to have a superabsorbent that you can either use to protect the seed or have in the soil to maintain the water. So our idea and concept initially was very simple. We simply want to control the water cycle. And in agriculture, you have the water cycle, you have the carbon cycle, and the nutrient, that means nitrogen and phosphate cycle. So we wanted just to work on the water if possible, and you will see. So now in industry, we have some commercial product, and basically these are the superabsorbent. They are based on acrylamide or acrylate. So it works very well, but there are 2 problems. The first one is they're not biodegradable. The second is the degradation product, when eventually degrade, are toxic for the soil. So we cannot really afford to poison the soil. So we want to replace that. So let's see what we can do. So here our experimental plan is fairly simple. Basically, we start with the tree. Out of the tree, we use a pump. This is a same nice pump than you do in your mill, a highly bleached pump. And then here we do a tempo treatment. Basically, we want to disrupt the hydrogen bonding network to replace the OH part carboxyl group, and we can put them under the sodium, calcium, potassium, zinc, and whatever form. So we can control basically the counter ion, and we do that by homogenization. That means we take the pump and we pass it through a little capillary, so there's a lot of shear, and basically we just remove each of the fibril, and that's defibrillate the cellulose into nanocellulose. And this nanocellulose in water forms a gel. We can form a gel with between 0.1 cellulose to 1%. So it's mostly water, it's mostly hydrogel, and we dry it, and that's what we use as agriculture aid. So that's how we prepare the gel. And here we did a bit of work, and we work here. This is with the spinach. We try a few crop. So here we have 4 replicate, and what we have is using 0.5% of commercial superabsorbent. We see it's really working well. Here is my control. That means if you just put the seed and you have it, so you see a big difference. And after that is the control with the fertilizer, and we use the same fertilizer for everything. So we see it really makes a difference, and the biomass is more solid. And here, these are our experimental results. We use 0.5% nanocellulose and 1% cellulose. So what do you notice here? That's visual. What does it tell you? Have we succeeded or have we failed? Any volunteer? You're very polite. We failed because our nanocellulose is not even as good as the control. And the more we put on nanocellulose, the worse it is. Why? What's going on? Is our concept flawed? And what we wanted to do is just to control the water loop. So let's look at what we've done. So basically what we notice is I show basically I measure, so that means out of here, we're going to take the biomass, we're going to look at the biomass wet and dry, and we're going to look at the respiration of the microorganisms in the soil. So if I look at the biomass, if I look what we have is the most we have is with the commercial superabsorbent, and I would say it is much higher than the control with a little bit of cellulose. It's not really good. And the worst that we have is with the nanocellulose. So we really show that we didn't do well. Why? So here comes our hypothesis. So what we try to do is we want to grow a plant. And the way we do that is we're going to put in the soil the nanocellulose superabsorbent. But in the soil, we have all kinds of microorganisms. And if we put some carbon, it will feed the microorganism. And basically, they will eat this carbon, and they will have basically to consume all the carbon and probably some nutrient in the soil. So if you put that, basically, they will have the carbon, but they need some nitrogen. And they would take the nitrogen that is probably was used by the plant during the competition. And so that means we have a proliferation of the microorganism at the expense of the soil nutrient. So basically, that is our hypothesis. Our hypothesis is to put some more carbon. That is a very accessible carbon. And what we do, we create a big party of the little microorganisms that just proliferate and consume all the nutrient, basically starving the plant. So what we decided to do, so our hypothesis, we wanted to test that. And for that, we will look at the respiration of the soil. So we grow the plant and we put the soil under the control condition, and we measure the CO2 emission. That means if you take some glucose and oxygen in your microorganisms, they will produce some CO2 out of breathing. And that's what we look. And effectively, what we found is the highest production, the production of CO2 is with our nanocellulose, and the lowest is with basically the control. So we really show that we have the microorganisms that are stopping the plant. And it is a bit humbling and it's a good lesson for us. What we wanted as engineers, we just wanted to look at the cycle of the water. And we say, oh, we're going to deconvolute the cycle of the water from the rest. But we cannot do that because if we use some carbon, we affect the carbon cycle and with the water, and with the carbon, both affect also the nutrient cycle. So the lesson of that is we cannot simplify like we did. We need to look at the water, the carbon, and the nutrient cycle for the plants. And that's basically what we learned in our engineering solution. Was a little bit too simple. But there's a lot of potential. Now we understand and you can reach the same level. So what we're trying to do is we're trying to control the degradation of the nanocellulose gel. So we use some cross-linking, we use some lignin to go much slower and to control the rate of biodegradation and the rate of emission of carbon in a controlled way. And that's where we are now. And hopefully next time I'll be able to show you the new results with the progress. Let's shift gear. Let's go on something we're a little bit, I would say we've been working for longer and we had a bit of success. I'll show you that last time, and I'll show you some basically development and how we can create some platform to get commonality. So here I show you a product that is commercial, that is a blood tapping test, and we make it out of paper. So basically what we have here is we have a little window, 2 pieces of plastic that will distribute the blood. We have paper under which we print the antibodies on here, and underneath we have some superabsorbent that will absorb the liquid. And this is in a casing of plastic. Here it is PLA, but we'll discuss that a little bit later. So why paper? Basically, we use paper because paper is great to transport water. It's also a good water resistant. We can make it hydrophobic. We can control pretty much all the properties. And also, and here I show you, we have the paper, you can control the fibers, you can have nanoparticle, control the size of nanoparticle, you can have surface treatment and control how deep it will go. And the polymer that you put here, you can have it assemble and control the domain. So you can do pretty much whatever you want with the current paper technology. And for the paper, it's easy to make. It's a roll-to-roll technology, so it's a continuous process. And it offers it's very efficient engineering-wise, and you can really control the structure of the material. So it's something very ideal from the material engineers. And you must have seen a lot of people were done with that. You can have the one dimension, you put a droplet of whatever you want to analyze in goes. You can have an go in two. You can have the paper that you fold and the origami, you put a droplet of water here, it will distribute and go all over the place. So a lot of work has been done, but at the end, it's just complex, and too complex. And when you go medical, when you go in the hospital, you don't want to have the test working 1 out of 10 times. You want 10 out of 10 times to get the results. So what we decided is to go for simplicity and robustness. So our strategies, instead of going for complex, is to go for simplicity. So no microfluidic, no moving part. We want something robust. I want the diagnostic to be able to store for 1 year. I want the end user, that means each of you in the room, to be able to do your own test. Let's say if you have to test for blood or for whatever condition, you don't have to go to the hospital, blood. I want you to be able to do that in your kitchen. It has to be easy to manufacture and low cost, so roll to roll. And at the end of the day, I don't want to contribute to the sustainability problem. I would like to be able to dispose. So it has to be all cellulose and I need no plastic. So that's what I'm trying to do. That's really the objective. So I will show you an example. I showed you that last time. Please, I'm going to show you 2 drops of blood. If you don't have blood, close your eyes 20 seconds. Sounds good? So I'll give you basically how it works. So basically, you put a droplet of blood over the test, and you have a system of window that distributes the blood all over the place. And we leave the blood in contact with the paper for 20 seconds. After that, you use a saline solution basically to wash it. And you wait. And after, when it's washed, what you see, it prints the group or your blood group. And there's no magic in that. It's very simple. We printed the letter A with the antibody A, the antibody B here that you see closely with the antibody B, and the rhesus is the bar here. And if it's not O, we have basically both antibodies and it makes a cross. So that's basically what we've done. Sorry. So what happens here? So when we have a positive, so we'll go when we have a positive, and I'll go here. No, I don't. Sorry. When we have a positive, what we want is the blood becomes your ink, and you want all the blood particles to form methyl agglutinate and to be filtrated by cellulose. And basically, we would print on the paper. While if you're negative, you want the cell to just go through the paper and basically to disappear, making the paper white. So that's the concept. So negative, that means if my antibody doesn't react with the antibody, I want them to go through. And if they react, they will collect the antibody, coagulate, because it will link that, form a little trunk that will be filtrated by paper. And here I show you in real size. In real size, this is the size of the paper, and this is in real size the size of the red cell. So the red cell, really, they're designed, the paper is designed such as it will just go and flow through, and we really need to agglutinate that in order to keep that. So for a negative, we want, this is my paper network, I want I want all the cells to go through, so I want the paper to have pores big enough to let all the cells go through, while for the positive to be retained. So that's basically the first test we have. And that is being commercial, and hopefully it will be done to million a day very soon. Out of that, we had the industry that came to us. And basically what they wanted is for us to develop a fibrinogen paper diagnostic. So why is it used for? So if I have a car accident and I have a trauma, that means I bleed, and the ambulance will come and they will have to make within seconds make a decision. Is my fibrinogen level normal or is it too low? If my fibrinogen level is low, that because I'm in a shock, I lost too much blood, or my liver stopped to do some fibrinogen, basically I have nothing that coagulate the blood, and I would just bleed to death, and they can do and inject me as much blood as they want, nothing will go. My fibrinogen is too low. So what they need to do is to take a syringe, inject me a massive dose of fibrinogen, the same as if you have a epileptic reaction allergy, we give some adrenaline. So that's what they have to do. However, if I'm bleeding, but I'm not in a shock, and my liver still produces my fibrinogen, if you give me a massive dose of fibrinogen, then you put me in a shock, I would stop producing fibrinogen, and then I will bleed to death. So basically, the people, the flying ambulance in Australia are asking us to prepare something, and a little diagnostic they can bring over, so it will be used for car accident. Here I show the sharks on our beach, so that's a kind of element, things go fast. And what we need to do is my fibrinogen level above or below 2 grams per liter? 2 grams is the critical level. Lower than 2 grams, inject. Higher than 2 grams, do nothing. And what we like is we test lower, inject a bit, high is it, inject a bit, and so on. So to have a kind of a thing. So that's basically the concept. So how can we do that? And here come Merrick, and Merrick work on that. And basically what you notice is if you use thrombin, thrombin is an enzyme. And all does thrombin is it will take 2 chains of fibrinogen and it will polymerize that into a single chain of fibrin. So that's what the thrombin does. It's an enzyme that polymerizes. However, what we notice is what Merrick noticed is the thrombin, the fibrin is significantly more hydrophobic than the fibrinogen. And what he did is we prepare some little film. If you have cellulose, you have a contact angle of order of 30-ish. If you have cellulose fibrinogen, the same, and a thrombin. But if you have cellulose with the thrombin that is formed by the polymerization, it's much more hydrophobic, it's 110. So that's what he noticed. So out of that, what was the idea? What can we do? So basically, Merrick's idea was to take a sample of blood, mix that with thrombin, add a droplet to paper, wait something like 20 seconds, and have to put the paper with the thrombin in water with a dye to mark and see what is the elevation, what is the capillary force. And that's what he did here. So if you have basically paper that is mixed with fibrinogen of different concentration, without thrombin, it's just the same height. If you use thrombin to polymerize, and basically that shows you the effect of the fibrinogen concentration. If you have 0, it's very high, 0.25, 0.5, 1, 2, and 4 grams per liters. And here basically I show you the elution height. So basically this is this height as a function of the fibrinogen concentration. So if I have nothing, basically no thrombin, it's very high. So there's no hydrophobicity. But this is the correlation sheet that I have with my fibrinogen and thrombin. And the zone I'm interested is a 1 to 2 grams per liters. you can see it's very sensitive. So out of that, we're able to create a test, a concept of a test to measure fibrinogen in blood using the paper strip. However, there's a trick. Here, basically, we work with plasma, and plasma means blood in which I remove all the cells. So it's not direct, so it's a little bit too difficult. So in another concept, Merrick developed a test to work with paper with the real blood. And what we have is you put the blood and you mix with the thrombin, the enzyme, and you have a paper strip here that will just touch. And by capillarity, the paper will filter this paper, the red cell, and just let the plasma go through. So we develop a one-step prototype. Now, this is not really practical. We have to engineer that in a diagnostic the same way as what we did with the glyph, the blood test. So this is the second example of a paper diagnostic. I will show you another one, and what I want to show you is to show you that paper is an exquisite material that is very uniform, and this is the work of Macon on wicking. So here what I do, I put a droplet of antibodies on paper, I wait a bit, and then put a droplet of blood. And if my blood is specific to my antibody, it forms some agglutinates, and what we notice, it doesn't wick as much in the paper. So that means if you have a positive, you have a small stain. If you have a negative, you have a big stain. And what we do, we look at the area as function of time, and this is the negative. So this is here. So not only at the end, we have a bigger, but the kinetics is slower. And this is a positive. So we did that with blood tapping. So here we have one graph with the antibody A and with the blood. But we did the very same with COVID. We used the COVID anti-SARS-2 antibodies on paper, and we add the blood, and we found the same. This is the curve indeed for the COVID. So this is the fastest COVID direct test, and you have that in 15 seconds directly with the blood. So that's a second example. After that, Macon worked a bit with basically the paper and the composition, and what we found is the area is really a function of the volume. So the paper is extremely regular. You have such a good formation, it's so uniform, then it's very accurate measurement. So that's basically the message of this graph. And we work a bit on blood. What we wanted is to look at how the blood dries in order to provide guidance on the concentration of red cell, basically to make an anemia test just by looking at the cracking pattern. So we had a bit of work on that. And finally, we need to model. And what we wanted is to model the coffee ring, because here you notice we form a coffee ring. As the blood dry, we wanted to model that. And that's what we did that from first principle with a bit of a differential equation. And what we relate is the formation of a coffee ring is directly proportional to the wettability. So if you have a low contact angle, you form a coffee ring. If you have a high contact angle, you will not form some coffee ring. And we did that by modeling. So just to show you that the phenomena is colored chemistry, it respects the mathematics and we can model. Good. A few examples of what we can do with cellulose. And here I give you an example of nanocellulose. I talk about the blood test. And if you do a blood test, basically what you have is you have a little cartridge and you have little beads of gel in which you have the antibody A for the A, B, and so on. You put the blood. And basically, you mix. If it's positive, it forms a little aggregate, and that means when you centrifuge, it forms a bar at the top. If it's negative, it's good at the bottom. And typically, these are the little bits of polyacrylamide. We wanted to do that with cellulose gel, and that's what Rodrigo did. So here we did that with the positive, and we did that with the gel. So that's 0.1, 0.2, 0.3% concentration of gel. And you see at 0.3, we have some fairly good results. We have a bit of lysis of cells, so we really have to control the ionic strength. So we did a bit of work in order to be able to crossing the gel because I need some salt without affecting the ionic strength, which will lyse, which will destroy the red blood cell. But my point here is we can use nanocellulose gel for biomedical application for diagnostic here. That's the common test that is used all over the world. I told you we did the same here with the COVID. So we use the same gel card, but instead of having the antibody from the blood tapping, we use an antibody that is specific to the antibody, the virus antibody of the SARS. We craft that to a droplet of red cell, and that's how we did. We did a test also that can be developed using the same equipment of as the blood test. So all that to show you that out of cellulose and using the biorefinery, we can go pretty high in the biomedical, I would say, sphere. And the last example is I showed that a bit at the last time is to make a nanocellulose gel to grow some organoids. And typically this is done with what we call the matrigene, that is done from the tumor of a cell, of an animal. So basically for the matrigel, we take rats, we inject them a substance that creates a tumor, and we extract the tumor for the gel. So that's how the gel is done. And we need something like 10 milliliters of the vial for a test for cancer treatment, let's say. So it's very expensive and not reproducible. And what we wanted is to do that with cellulose, and that's what will work. And here I show you example with the colon cell. Like if I have a colon cancer, or we suspect I have one, the surgeon will take a biopsy and will grow the different type of cells, separate them, and try the different type of drugs on it. And for that, they need to grow, and they use this matrigel. So we wanted something that instead of costing $1,000 a dose, would cost a few cents. And that's what we will work on with the nanocellulose gel. So this is the nanocellulose gel, and you see in green is the organelles alive, and in red is dead. So you see just by itself, everything dies because it doesn't have the nutrient. We control first the ionic strength with the glycine, and with the glycine, it's okay, but you know, it's getting better. And then we use glycine as a protein for the substrate, and we graft another protein on the gel to help the organelles to deposit on the cell. And basically what we find is that means everything is alive, nothing is dead, and we get pretty much the same as a commercial product after 2 days, after 4 days. After 4 days, we have a little bit more dead cell, and you can see we have one cell too, that basically the tissue start to grow organs. So that's basically what Rodrigo has done. So I will stop it here for the paper diagnostic. What I wanted to show you is hopefully that paper is a very performant material for diagnostic. The formation of paper on a modern paper machine is really exquisite. The formation, the regularity is exceptional, and you can really use that for higher advanced function. And what we want to do now is to make everything out of cellulose. I want to replace the casing with hydrophobic paper. I want to replace the little window with the clear nanocellulose film, and so on. And we have to change the mentality of the paper industry. And in this paper industry, we want to see how many million tons do we need. And it's not a matter of tons that we count, it's the value. At the end of the day, we must sell for a few $1 million of product. Whether we do that with 1 kilo or 100 tons, I would say it's two different business propositions, but we go for profit. And if you go with biomedical, you can have a small scale and high profit. And that's what we're trying to convey to our partner. So this is the second part of my presentation. And now we'll show you a little bit of flash of cellulose to present you cellulose under a different optic. And I want to show you what are some of the possibilities we can do with cellulose, that kind of a cool chemistry materials. I will just show you a few examples, and then we will finish the talk, and I will welcome your questions and your comments. So let's start. So the first one is we talk a lot about nanocellulose, and then nanocellulose, basically what we want is we have the pulp, the bleach pulp, and what we want is to oxidize my hydroxyl group. I want to disrupt my hydrogen bond that keep my cellulose really, really close. I want to break that down. And the way we do that is we're going to react the C6 of the hydroxyl into a carbonyl group. So that means carbonyl under the sodium form that will swell and weaken the hydrogen bonding. So when you put in a homogenizer, when you put some shear, you just dislodge each of the fibers. So that's what we do. But basically the tempo just react with the C6. And what we like is to go much higher level of carbonyl content. So for that, we develop a reaction with the periodate, and we play a bit with the chemistry to do everything in a single pot. And if we do that, we can go to much higher level of a carbonyl group, much higher charge, and actually some of the benefit what we can do with that. So one of the applications that we look is to develop click chemistry. So click chemistry, basically, it's a kind of a standard chemistry. So I'll have I can have basically whatever big you need and I want, and I will have and put the amine function of my cellulose, and then the two will react by kind of a click reaction, and that will allow me to have very big group that are typically steric, unstable, and with the click chemistry we can put some big group. And what we've done, so this is with our friends from AgroParisTech, Professor Florent Allais. What we've done is we grafted some UV absorbent unit that were extracted from plants. And you have all the collection, and we use the click chemistry to try all the different compounds. And here what I show you is the performance. I show the absorbance as function of the wavelength. So here we adsorb, so we can see that in the UV, so that means in the wavelength between 250 to 400, the compound are extremely efficient. We adsorb all the UV at a low concentration of the products. So it can be very efficient. And what I didn't tell you is we craft this UV absorbent natural molecule onto nanocellulose crystal. So we have a small little rod on which we have this big UV absorbent molecule, and we graft by click chemistry. And we did a click because we have one tap, it's like, and then we can put whatever type of molecule that we want. So let's look at a bit of the performance. So the first study that we did is we used this nanocellulose crystal under which we put the UV absorbent molecule that was extracted from the mustard plant. So we did that, and we formed some film, some polymer film. So this is polyacrylate or polystyrene, and we were able to absorb most of the UV. So we make UV absorbent plastic, and because the nanocellulose is smaller than the wavelength of light, it remains clear. So what you have is the PVA, polyvinyl alcohol, the nanocellulose, and with the nanocellulose that is functionalized with the UV absorbent, and it is all are clear. It's a little bit more yellow, but it absorbs pretty much all the UV, and the UV resistance of the polymer is much higher. Another application is, instead of going for composite, we can use that for cosmetic. And here we use the same UV absorbent grafted to my little crystal of nanocellulose, and we develop some sunscreen formulation. That means if I want to, the sunscreen, the nicest for the skin, or water-based with glycerin. And for that, typically the synthetic organic sunscreen do not disperse well. So we wanted to use the nanocellulose crystal to nicely disperse from a base and keep the UV absorbent. And this is what we've done. So basically, if we have, this is the formulation, the glycerol and nanocellulose, so it's really transmit everything. While if you put the molecule, it absorbs all the UV in the UVA, UVB, and UVC in this region. So it's very effective, and there's a company in France that is working on commercializing the concept. Good. So now that was for the nanocellulose, the cellulose grafting and the application. What I will do here is to show you what we can do with the cellulose form. So here, this is the work of Lila, and we take basically the pulp. We're going to form a gel using the tempo reaction and homogenization. We have a gel, and then we're going to freeze dry the gel into a foam. And what we want is to replace the adsorbent in food packaging, the adsorbent in the diapers, and also for some diagnostic. Instead of polyacrylamide, we want to use cellulose gel. So that's what Lila has been doing. And here we have two types of gel. We have the normal nanocellulose with the tempo, and we have carboxylic group of 1.3 millimole per gram. And we can increase that by 50% with the periodate chemistry that David did. And here what we do is we have the little subadsorbent, we have it plunge in water, and we measure how much water we absorb as function of time. And we have a camera. We also look how big is the stain of the water. So we measure and we see how much we absorb. So here we look, this is for the high concentration, the low. We look at the size of the stain and the absorption. And what we notice is the absorption is much higher if you have the high capacity. So we have better superabsorbent. And that's basically, we correlate that with the pore size of the porosity of the material. So if you have a higher carboxylic group, you form many more smaller and more uniform cells that absorb the water initially faster and after a little bit slower because we have less reservoir, but the capacity is higher. So that's what we basically did. We worked a lot also on the nanocellular. Just put that, this is a bit of action here. And you see with the leader. So what we have is basically a template. We have little groove, and under which we spray some nanocellulose fibers. And basically what we try to do is to pattern. That means we want to have this type of pattern of nanocellulose, and we look at the dimension of what is the width and the depth on the properties of the fabric, the material we do. So what we have is very patterned is in the macron dimension, and we do that to control the flow for macrofluidics, or also to create some artificially hydrophobic surface. So that's how we control the roughness. The last example that I will show you, it's with nanocellulose crystal. It's really biodeformed. This is a work of Mauchi that finishes PhD and Bikram. So we'll make nice films, and we can make films of different colors. They're translucid, and we can go from the blue, cyan, and green color. And what we do is basically we have a suspension of CNC, cellulose nanocrystal in suspension. It forms a liquid crystal solution and with a chirality. So all the crystal organized in a spiral. And the distance, half of the pitch of the size, basically the wavelength, the light will be absorbed will absorb the wavelength of half of the pitch. That means if I have half the size of the pitch is of 500 meters, it will absorb in the 500 meters and basically show the colors. So by controlling the pitch, basically the structure of my liquid crystal, I can form clear films that absorb different colors. So we have a bit of work on that to create cellulose of different color. Or we can have a polymer that absorbs water, and basically depending on the amount of water that is absorbed, it's a humidity indicator. It can go from red to green as depending on the color, the quantity of water. Or we can use that with biomolecule to change the pitch and to give a visual signal. That means we'll have the cellulose that will go from, let's say, green to red, or give red or green, depending if you have a positive or a negative. So that's what we're trying to do. We want to link with the diagnostic and to have a cellulose visual indicator by changing the color. So that's what we've been doing. So I kept you for already an hour. So now I hope I convinced you that the biorefinery is really exciting. I hope I convinced you that it already plays a big role in Indonesia, with 17% of the export coming from the biorefinery. And I wanted to show you that we can do much more. We can really use the science and engineering to develop all kinds of new products of high value and products that you cannot do with the normal petrol refinery. So that's what I want to do. And now I hope that some of you will come and collaborate with us and visit us. And when you come in Austria, there's a key question is, are you of the beach type or the desert type? So please come visit. And on that, I would stop my presentation and welcome your questions. Thank you.